Hello everybody, and welcome back to Physics 425. So what we've been talking about lately is different methods of heat transfer, and we've kind of finished that discussion now. And so what I want to do is switch gears and move on to the next topic, which is a big topic. Ultimately, what we'd like to do is be able to understand how we can reach temperatures as low as 10 millikelvin. And the method is going to be by using dilution refrigerators, which involve mixtures of helium-3 and helium-4. And in order to fully appreciate how dilution refrigerators work, we're going to have to really tackle a number of different topics along the way. And so what I wanted to do is I wanted to start by writing out a little roadmap that we're going to try to follow for the next little while. And so step one is going to be to understand the difference between the behavior of systems of identical particles at low temperatures. And so specifically, it's going to be understanding the difference between systems of fermions and bosons at low temperatures. And this is going to be important because when we are dealing with mixtures of helium-3 and helium-4, the helium-3 particle is a fermion and the helium-4 particle is a boson. And so in order to properly do that, we're going to have to do some quantum mechanics review. We're going to have to develop the wave function for a pair of identical particles. What we'll see during that process is that when we develop that the wave function, we'll be able to really deduce immediately the Pauli exclusion principle for fermions. And that's one of the important things that we're going to have in our toolbox for proceeding. And then we'll also write down the so-called distribution functions. The distribution functions for fermions and bosons. I hope we won't derive them in this part of the course, but what I hope to do is derive these later in the course. Okay, so that's step one of our roadmap. Step two is once we know something about fermions, what we're going to do is we're going to examine their behavior at very low temperatures, near the ground state of the system. So systems of fermions at low temperature. When we do this, we will run into things like the concept of the Fermi energy, we'll have to make use of something called a density of states. And we'll use these things to calculate the low temperature heat capacity of fermion systems, as well as the low temperature entropy of a system of fermions. Okay. Once we've done those first two things, then we'll be able to start discussing mixtures of helium-3 and helium-4, the two isotopes of helium. We're going to come up with an interpretation of chemical potential. What it's going to be related to is the change in energy of a system that results when you change the number of particles in the system. We will examine the energetics of helium-3 and helium-4 mixtures. And we will relate the Gibbs free energy to chemical potential. Okay, and then finally, after doing all that, which might take a few weeks, we will then be able to discuss the dilution refrigerator. We'll talk about it in terms of an analogy with evaporative cooling. So we've talked about evaporative cooling when we pump on the vapor pressure of, say, the helium-4 gas above the surface of the liquid. What we'll end up talking about is evaporative cooling by circulating helium-3 through a mixture of helium-3 and helium-4, where we have a helium-3 rich phase and a helium-3 phase that a phase that is depleted of helium-3. And when a helium atom moves from the rich phase to the depleted phase, that will be analogous to evaporative cooling. Okay, so we'll be able to estimate the cooling power of a typical dilution refrigerator and use that to calculate a base temperature. And then hopefully we'll go through like a little overview of the operation of a dilution refrigerator. Okay, and so you can see there's lots of topics that we have to get through in order to do all of this. And so let's begin. So the first step on our roadmap is to start to talk about identical particles. For many of you, or for some of you at least, this may be a review, but that's okay. Okay, so the first thing that we'll start with is acknowledging that classically we can always distinguish between particles. Okay, we'll see, I think, a pretty simple case where this is not always possible. In the case of quantum mechanics. So let's consider a simple example. So we'll have two particles, and so maybe over here we start with particle 1, and over here we have particle 2. Actually, I'm going to move it I'm going to move particle 2 over here. And so initially, these particles are kind of approaching one another. There's going to be some kind of interaction. They're going to scatter off one another. And so one possible outcome is that they come in, they have a distance of closest approach, and then they scatter away. So maybe at different times along their trajectory, particle 1 follows this upper curved path, and particle 2 follows this lower curved path. Okay, well, we could have a similar scenario where our particles start in basically the same initial positions, and they're going to again interact with one another. There's going to be some kind of scattering event, but maybe this time what happens is they scatter off each other in a slightly different way. And so at different times, particle 1 is following this type of path and ends up over here. And particle 2 follows this kind of path and ends up over here. And so if you look at these two situations, they have similar starting positions. The starting positions are particle 1 in the top left corner, and particle 2 in the bottom right corner. And so you have this situation, and then you end up with, in one case, particle 2 over here, and in the other case, particle 2 over here, and particle 1 over here, and particle 1 over here in this second scenario. And so if these were non-identical particles, right? One is a proton, and the other one is a helium nucleus, an alpha particle, then you can always distinguish between the two. If this was classical physics, then even if the particles were identical, you could always distinguish between these two scenarios. And so let's call this top scenario A and the lower scenario B. So classically, we can track the positions and momentum of particle 1 and particle 2 with arbitrary precision. Right? So if these were, even if they're identical golf balls or something, we can always, and they're moving really fast, we can always get a high-speed camera, and we could track both the position and the momentum of both of those balls with as much precision as we care to. And because of that, we can always distinguish between the two particles. Distinguish between the two particles at all times, and therefore distinguish between the two scenarios, A and B, even if the two particles P1 and P2 are identical. Okay, but in quantum mechanics, we have an uncertainty principle. However, because of the Heisenberg uncertainty principle, Heisenberg uncertainty principle, which you know is that the product of the uncertainty in position and momentum is greater than or equal to some constant h bar over 2. In quantum mechanics, cannot always tell which particle is which after the scattering event. Okay, so if we were to say that delta x is something like this, and so this is the distance over which we start to lose the ability to distinguish the two positions of the particles, then all we can do is say, if they're identical particles, is we started with a particle in the top left and bottom right position, and then there was some scattering event that we couldn't observe with arbitrary position, and after that happened, there was a particle in the bottom left and top right positions. And if they're identical particles, I can't tell you if after the scattering event the particle in the bottom left is P1 or P2, because it looks identical to in each case. And so the same is true in scenario A. After the scattering event, we have a particle in the bottom left and the top right, and I don't know which one is which. And so, as far as we're concerned from observation then, the scenarios A and B are indistinguishable. We don't know which type of scattering event occurred. Okay. So, if particles come within delta x of one another, we lose the ability to distinguish between the two, and therefore between scenarios A and B, because scenarios A and B have the same initial conditions and the same final conditions. Okay, so what this implies that when we have identical particles, exchanging the positions of P1 and P2 leaves our system unchanged. There's no measurement that you could do that would be able to tell you whether or not two identical particles have swapped positions. Okay, so that's the first useful insight that we can look at. So the next thing, let's just remember some basic facts about quantum mechanics. In quantum mechanics, physically measurable quantities in quantum mechanics are determined from the absolute square of the wave function. So you're familiar with some examples of that. If I was to evaluate the wave function for some particle and I squared it and multiplied by dx, what this tells me is the probability of finding the particle between x and x plus dx. Okay, so that's something you could do. You could set up a system in an identical way over and over again, and then at some moment in time you measure the position of that particle and you repeat that measurement over and over. You can make a probability distribution of finding the particle between x and x plus dx, and that physically measurable quantity is proportional to the square of the wave function. Okay, another thing you could do in the Bra and Ket notation is you could evaluate the expectation value of the Hamiltonian, where if the wave function is an eigenstate of the Hamiltonian, then that will tell you the energy. And so what this Bra and Ket notation tells us, remember, is that we're going to take the conjugate of the wave function multiplied by the wave function, and then we're going to integrate that over x, which is the integral of the square, the absolute square of the wave function. Okay, and so again, this physically meaningful quantity involves the square of the wave function, and so this is the expectation value of the system energy. Okay, so for a system of two identical particles, we argued that we are going to require that if I have the wave function for a system of two particles, and so let's define the meaning of some of this notation here. So the first position inside the brackets is going to represent particle 1. And so this is particle 1 at a position x1, and this is particle 2 at a position x2. And so what I want to imagine is that we swap the positions of these two identical particles. And so now what we're going to do is we're going to say particle 1 is at x2 and particle 2 is at x1. And because we said the exchange of identical particles leaves the system unchanged, and we know that physically meaningful properties of the system are determined from the square of the wave function, then the squares of these two different wave functions with only the positions of the particles exchanged must be identical. And so this is particle 1 at x2, and this is particle 2 at position x1. Okay, so in words, since particles are identical, like two electrons or something like that, the probability of finding P1 at x1, or strictly speaking, P1 is at a position between x1 and x1 plus dx1, and P2 is at x2 is the same as probability of finding P2 at x1 and P1 at x2. Okay, so this requirement or this condition is satisfied if, so let's take our wave function where we have, say, P1 at x2 and P2 at x1, and we're going to say that that's equal to the wave function with particle 1 at x1 and particle 2 at x2 to within a phase factor. So where e to the I delta is a phase factor. You can see that this must be true because these probabilities that we calculate involve the square of the wave function, and so if I was to square the starred wave function, so let's label this as star, we would have that phi x2, x1 would be equal to, say, the conjugate, but the conjugate is going to change the sign in front of the phase factor, the I, which is the square root of -1, and then we would have x1, x2 conjugate, and then e to the I, this would be e to the plus I delta, and then phi x1, x2, and then of course those cancel, and what we get is the requirement that the square of these two wave functions with the particle positions exchanged are equal to each other. Okay, so I want to see if we can come up with a bit of a restriction on what this phase factor has to be. So to do that, we're going to define an exchange operator. So the exchange operator we're going to label as P12, and what it does is when it acts on our two-particle wave function, it just swaps the positions of the two particles. And so the exchange operator acting on the wave function with P1 at x1 and P2 at x2 yields the wave function with P1 at x2 and P2 at x1. But what we just argued is that this must be this e to the I delta, this phase factor, times the original wave function. Okay, so that's fine. Let's do now another thing. Let's take the exchange operator and we're going to act on our wave function twice. So let's do it this way. Okay, so let's do this in a few steps. We know that this is going to be phi x2, x1, and so this is equal to P12 phi x2, x1. But we know that this is e to the I delta phi x1, x2. And so what we have is then e to the I delta P12 acting on phi x1, x2. Okay, and then we just keep going. Well, we know that this is phi x2, x1. And so what we have is e to the I delta phi x2, x1. But then again, we know that this is e to the I delta phi x1, x2. And so that must mean that this is e to the 2I delta phi x1, x2. Okay. But of course, if you think about it, it must also be the case that if I take my exchange operator and I have a two-particle wave function and I act on it twice with that exchange operator, then the first time I act on it, the two particles get exchanged, and then the second time they get exchanged again, and so they're back to their original position. And so we must just end up with the same wave function again. And so what we've got now is two expressions for the same quantity for our original wave function acted on by the exchange operator twice. And so our two results, of course, must be equal to one another. And this equality only holds if our phase factor, it's actually the square of our phase factor, is equal to 1. Equivalently, we could take the square root. The square root of 1 is plus or minus 1. And so e to the I delta must be equal to plus or minus 1. Let me just remind you of Euler's identity. E to the I delta is cos delta plus I sine delta, and we want that to be equal to plus or minus 1. This is true if delta equals 0 or pi, or any multiple of pi. Because if I put in 0, cos of 0 is 1, and sine of 0 is 0, so we get the plus 1. If I put in pi, cos of pi is minus 1, sine of pi is 0, so we get the minus 1 result. Okay. Well, actually, let's step back here. And so e to the I delta must be plus or minus 1. And so if we go back to this equation star, and we use that result in here, then e to the I delta must be plus or minus 1. And so that's phi of x2, x1 is equal to plus or minus phi of x1, x2. Okay, so returning to star, we find that phi x2, x1 must be equal to plus or minus phi x1, x2. So either exchanging two identical particles leaves the wave function completely unchanged, So phi x2 x1 is equal to phi x1 x2, or it introduces a negative sign. So those are the two cases. If the exchange of particles leaves the wave function unchanged, the wave function is said to be symmetric. It will turn out that bosons have symmetric wave functions, and if the exchange of identical particles introduces a negative sign, the wave function is said to be antisymmetric, and identical fermions, or fermions, will have antisymmetric wave functions. Okay. All right. So let's keep going, and let's suppose that our system is two identical and non-interacting particles. So non-interacting means there's no potential energy between them. And so, for example, this might be a pair of particles in a box, or a 1D infinite well, or something like that. Okay, so we can write down a Hamiltonian for particle 1, and let's call that H1, such that if I take this Hamiltonian H1 and we have a particle in state A, it's an eigenfunction of the Hamiltonian, and it has an eigenvalue or an energy EA, and then of course we get our wave function back again. Okay, so in this notation, what we have is particle 1 in state A with energy EA. Okay, now we said we were going to have two particles in our system, and so in the same way, the Hamiltonian for particle 2, which is an identical particle, is H2, such that when H2 acts on the single particle wave function of particle 2 at position x2, what we get is the eigenvalue, which is energy EB, times the wave function of particle 2 back again. And so this is particle 2 in state B with energy EB. Okay, so just for example, for free particles, the Hamiltonian would be just the kinetic energy, which is related to two spatial derivatives. And these wave functions, phi A and phi B, are the single particle wave functions of P1 and P2. So for example, if these were particles in a 1D box. The wave function would look something like root 2 over L sine of n pi x over L, where L is the size of the box. Okay, so we now have some requirements for our two-particle wave function. We've written down example one particle wave functions for a system of a single particle. What we're going to try to do is construct the appropriate two-particle wave function. So the requirement for the two-particle wave function for the net system of two particles I should say requirements. There's two that we're going to try to satisfy. One is the exchange property, that if we exchange the positions of identical particles, we get either plus or minus, a plus or a minus sign introduced. So this is the exchange property. The other thing we're going to have to satisfy is that if we act on our two-particle wave function with the Hamiltonian, which is going to be for non-interacting particles, just the kinetic energy of the two individual particles, we should get the energy of particle 1 and the energy of particle 2 times the original two-particle wave function. And so above we said particle 1 was in energy state EA and particle 2 was in an energy state EB. Okay, so this is the net Hamiltonian of non-interacting system. So we're not considering any kind of potential energy between the two particles. So what requirement 2 really is that this two-particle wave function that we're going to try to construct must be an eigenstate of the net Hamiltonian. Okay. And so let's just try some guesses. Our first couple are going to fail, but maybe that'll lead to some insights. So we saw above that the Hamiltonian was just the sum of the two single particle Hamiltonians. And so what if we just took our two single particle wave functions and added them together? Okay, and so here we have P1 in state A, and over here we have particle 2 in state B. Well, let's just test the exchange property. So we switch the particle positions. And so now we have particle 2 in state A. So this is P2 in state A. And over here we have particle 1 in state B. So P1 in state B. Okay, but that's not the same. Right, because we wrote down what these wave functions look like, and If we have the two particles in different states, then we don't have the original wave function. And so this fails the exchange test. Okay. So we can try another guess. So what we could do is, instead of adding the two single particle wave functions, what happens if we take a product? Then when we do exchange, we run into a similar problem. The two particles now have switched the states that they were in, and so this again fails exchange requirement. Okay, so what we want to do is we want to have something where when we exchange the particles, which particles were in which states is somehow maintained. And the way we're going to do it is we're going to try to combine the two approaches that we just did, this summing and product approach. So what we're going to do is we're going to say, let's write down a two-particle wave function in which we have, in one case, particle 1 in state A and particle 2 in state B, and we'll multiply those two. And then we're going to add to that the opposite, where we have particle 2 in state A and particle 1 in state B. In fact, we're going to plus or minus will turn out to work. And so what we've constructed here is a superposition of P1 in A and P2 in B. And so the superposition is that set as well as P1 in B with P2 in A. Okay, this maybe makes a little bit of sense if you think of it this way. This makes some sense because with identical particles, you wouldn't be able to tell which one, particle 1 or particle 2, if you somehow wanted to label them, was in which state. And so what we have then is a superposition of both possibilities. Because with two identical particles, one in state A and the other in state B, we can't tell which particle, whether it's 1 or 2, is in A and which is in B. Okay, so let's do the exchange here. Oh, sorry. Let's try the exchange. Okay, so phi of x2, x1. So wherever I see an x1 over here, I'm going to put an x2, and wherever I see an x2, I'm going to put an x1. And so what we get is phi a x2, phi b x1, plus or minus phi a x1, phi b x2. Okay, let's factor out the plus minus, and then what we get is, let's put the second term first. Phi a x1, phi b x2, and then what we have is plus or minus phi a x2, writing the first term, phi b x1, and that makes sense because if I was to take the plus sign, I'd get plus times plus, which is plus, and if I take the minus sign, I would get negative times negative, which is also plus, so that's okay. All right, but what we have in brackets here is just the original wave function, and all we have is a plus minus out front, and therefore phi x2 x1 is equal to plus minus phi x1 x2. And so the exchange requirement is satisfied. All right, we have one more thing to do, and that is to check that it's an eigenstate. Check that this two-particle wave function is an eigenstate of the total Hamiltonian h1 plus h2. Okay. So we're going to take h1 plus h2, and we're going to act on our two-particle wave function. Which we'll have to write out again. So particle 1 in state A times particle 2 in state B plus or minus particle 2 in state A times particle 1 in state B. Okay. So let's distribute the h1, and so h1 acts only on particle 1, the wave function of particle 1, and so it's the x1 cases, and so it's h1 acting on phi a of x1, and then that still has to multiply phi b of x2, and then we have plus or minus. And then phi a is the particle 2 wave function in this case, and then we have h1 acting on particle 1, which is in state B in this case. Okay, now let's distribute the h2 Hamiltonian. So we have plus, that's going to act on the x2, particle 2. So we have phi a x1, and then we have h2 acting on particle 2 in state B, and then we have plus or minus, then we're going to have h2 acting on particle 2 in state A, and then we have to multiply by state B with particle 1. Okay. So I think that's probably right. And so here we're going to get EA phi A x1. And here we're going to get EB phi phi b x1. Right, these are now, inside the brackets are the single particle Hamiltonians acting on single particle states, and so they are eigenfunctions. Here we have particle 2 in state B, so we get EB phi b x2, and then here we have EA phi a x2. Okay, so let's write things out and see what we have here. So the first term is EA, and then we have phi a x1 phi b x2. Then we have plus or minus EB phi a x2 phi b x1. Then we have plus EB phi a x1 phi b x2, and then finally plus or minus EA phi a x2 phi b x1. Let's do this in a couple steps. What we'll do is we'll first collect the common factors of EA and EB, and so we get EA, and then what do we have? Phi a x1 phi b x2, and then the last term plus or minus phi a x2 phi b x1. But if you look at what we have in the brackets here, ax1 bx2 ax2 bx1, that was just the original trial wave function. So that's phi x1 x2. And so what we have here, let's make a better brace than that. Is phi x1 x2. Okay, we still have the EB to do. EB, let's write the second EB term first. Phi a x1 phi b x2, and then the first EB term has a plus or minus in front, and it's phi a x2 phi b x1, and this is also the same trial wave function. And so therefore what we found is that when we take the total Hamiltonian and act on our trial wave function, two-particle wave function, what we get is EA plus EB times the original wave function back again. And so therefore our two-particle wave function is an eigenstate of the total Hamiltonian. So we've tried our two requirements, the exchange property and the eigenstate requirement, and both are successful. And so therefore what we have is a symmetric two-particle wave function, which maybe we call phi s x1 x2, and so that's the one that uses the plus sign between this superposition of the particles in the two different states. and then we have an antisymmetric two-particle wave function. That's phi a, x1, x2. It's the same other than the sign between the two terms. We have a minus sign for the antisymmetric wave function. And so written like this, you can see right away that the exchange property is satisfied, where for the symmetric two-particle wave function, swapping x1 and x2 leaves you with the identical wave function that you started with, no sign change. For the antisymmetric case, if you switch particle 1 and particle 2, you get the same wave function back except for the overall sign. Okay, so that's where we'll leave it for today, and then we'll come back and we'll work on the Pauli exclusion principle. Will be the first thing we work on when we return. Okay, thank you very much.